It's talking about a lot. It's talking about pockets and it's talking about it was into a lot of things. That's it.
Dang. That's awesome, because usually a lot of what we see, these people are like so famous now that what we see is what we see on like the documentaries and stuff. So
Get what we get.
yeah, exactly. Testing, testing. Perfect. And then how about this one? Able to detect it. We just started last month doing these workshops with like a hybrid model, because I recognize that a lot of students have like jobs and families and all these things happening.
Yeah.
So thank you for being patient with us, because we just got this little thing and it's a speaker and a microphone, because last time the speakers in the classroom weren't working. And so we were trying to figure out, like, I know we need some more technology to help us figure that out. So I'm happy that we got this thing here, because last time students had to walk over the iPad, which was like our microphone. And so
Yeah.
Not the way to go.
yeah. And I'm like, it's 2025. Help us. There we go.
Not that I want to feel more selfish, but I feel like that we should be more advanced than we are.
Yeah.
Just a little bit.
The classroom should have like all the technology you need.
Uh-huh.
Oh no, I did the door lock for Chris.
Oh.
It's not recommended.
Uh-oh. Okay, I think this might work. Okay, little mustache fixer there.
Oh, that's
Thank you.
and it's way better than the last time.
Yeah,
It
you like
is.
it? Okay, cool. See, we got the webcam, Chris, and then we have the microphone and speaker, so that students can talk, and when they talk in this direction, the speakers will be able to pick up their audio. That's the beautiful thing about this. And so now the only camera that we need to set up is the iPad, so that the speakers can see the students and the audience. Yeah, and that's it. We're all set up.
You tried to speak it already?
Yeah, no. But what you can do, what you could do actually is, if I join in through the iPad right here, you could like step outside and just talk and it should pick it up. We should be able to hear it here. So if I hit join meetings, this is, today's the 26th, right? Yeah. So yep, that's today. What should I start? Or should I put, let's try that, because either way it's gonna take me.
Recording
This, turn off the audio there. And then, stay co-host. You're gonna step outside, you're gonna hit this microphone, and you're just gonna say testing, testing, and then we should get a sense of how loud it is in here.
Okay, I will go back.
No, yeah. Because what happens is the audio from there acts as feedback when this microphone picks it up, so that's why I turn off the audio completely. A little like twos in there. I think he's muted because it says muted right here.
Yeah.
Can you help him
I think
click the button?
Oh my God.
I think it says, it shows up as muted on there.
Shows up what's that?
Muted.
There we go.
Testing, 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 1, 2, 3. Testing, testing, testing.
Is that a little too loud?
How's that? Oh.
There's a feature. Well, one of our speakers is here, Leonardo, so I will try to make this a little bit more.
Oh man, I feel bad. I can leave them. I really, I didn't have an exam today. Otherwise, I'd absolutely stay. Like I kind of want to stay actually.
I mean, you can join on Zoom while you drive, just to listen in if you like.
Oh, that's actually so intriguing. I'm worried about my battery though.
Yeah.
I really just want to hear I want to hear MJ's intro, and then I want to hear. Honestly, that's kind of the only thing I'm interested in. I shouldn't say that. That's what I'm most interested in.
She's gonna do great. She always
Oh
does
yeah,
great.
definitely.
I'm just trying to make it
I
like,
hope so.
do you think that's a good, where's the good angle? Right there?
If
Because we're gonna be right here.
for the one who's
Oh,
speaking,
Yeah,
I
for,
think.
yeah.
Are you
That-
gonna stand
that
on
looks good.
MJ?
I can see you from
MJ's?
here.
Yeah, right?
Mhm.
Yeah.
But you and I are
That's
about the same height.
Yeah,
Like,
so I think if I stand there, I think it's gonna cut.
do you want me
Yeah,
to
it is.
do that?
Because the monitor is really wonky.
Beautiful.
So we'd have to kind of do it with this.
Yeah.
How do you get both of you guys?
What's that?
If you're standing there,
I could just go like
Oh yeah,
that.
that looks.
or I can
That's
come
cool.
down a little bit.
And
like-
then
Yeah, I just could like ah.
you wanna
Yeah.
stand on a
How's this
stool?
Yeah, like it's something bad.
How about now, MJ? I put it down just a teeny tiny bit.
That looks good.
Yeah, that is good.
Yeah.
That is nice.
Yeah. That still looks good even for me too.
Yeah. It's good. It's kind of middle of the road.
Okay,
Okay.
thank you for your help.
Oh yeah.
Thank you.
Mm,
And I hope you have a great test. I hope it is super easy for you. And then, yeah, so now MJ, you can hit admit, for Leonardo. And then
um,
maybe.
I usually stop super fast, I like to go to McDonald's or something like that. But I'll stay like 10 minutes. Because I'm not gonna eat food today. Sure. On the way to work.
I think we have to.
Hi, Leonardo. Hi, Melissa. Good to meet you finally.
Hey, can you hear me?
Yes, we can hear you just fine.
Perfect, thank you. My team Melissa is also here, right? Hi.
We, we appreciate all of your patience because we used to only do these speaker series in person, and we're trying to kind of meet students where they are. And so we worked with the IT department, and they checked out equipment for us to try to do like a hybrid type of event.
That's fine.
So patience. Hi, Melissa.
Hey, how's it going?
Good to meet you.
Yeah, nice to meet you too.
Thank you so much for being here. We're gonna just wait a couple minutes for some students to come in through the room, and then we'll get started, okay?
Okay, of course.
Perfect, that's fine.
Cool. Thank you. All right, folks. So MJ is one of our peer mentors for the program. She's just gonna go ahead and introduce herself in the program, and then we'll go ahead and get started, okay? Thank you for being here again.
Good afternoon, everybody. Thank you for joining us today to our STEM speaker series. We are excited to have you here with us virtually. For those who can, consider joining us next time in person at San Diego City College Science Building, room S114. We also offer snacks and the chance to connect with the community and peers. So this event is made possible by our Title III HSI program known as Yo Soy STEM or I Am STEM in City College. Today we have the honor of welcoming two graduate students from UC San Diego. Please join me in welcoming Melissa Medina Peregrina and Leonardo Espinoza. My name is Mary Jane Garcia, or MJ for those who like, and I am one of the peer mentors for the program. The peer mentors, like me, help students be successful here in San Diego City College. So we help to connect them to important sources like tutoring and workshops that happen in campus. So thank you all for being here today. If you would like to stay updated with our events, please follow us at SD City HSI, or email us at city_yosoystem@sdccd.edu to be added to our campus class or to request information. Thank you.
All right. Well, thank you both so much for being here today. The whole point of us being here is to hear from your awesome stories. So I'm just going to go ahead and give you the proverbial microphone to either one of you first who would like to just dive in, talk about your background, what it's like to be a student at UC San Diego, and what it is that you're studying.
You wanna go first, Melissa?
Sure, I can go first. So give me 1 second so I can share my screen. I think you need to enable the option for sharing. Okay. Cool. So now you should be able to see my screen now, right? I think. Okay. What's going on here? Yeah. Okay, 1 second. Okay. So hello everyone. My name is Melissa Medina Peregrina, and I'm a third-year graduate student at UCSD. I do mostly is nuclear physics. At UCSD, they call it high energy physics experimental. So basically, in physics, you can either do like theory or experimental stuff. And I'm more inclined into the experimental stuff that I'm gonna tell you about in a bit. So the title for my talk today, I decided calling it Breaking Atoms and Stereotypes, a journey into neutrinoless double beta decay. So a neutrinoless double beta decay is basically the research I do, but when we talk about stereotypes, here it's, I guess, when I say I'm a woman and I'm into physics and I'm also Latina, I identify myself, of course, as a Latina, and into physics. These are two things that you usually don't hear when you go into physics. It's like very rare, and I think I just met once another, like in all my history in physics, I've just met only one girl that was also identifying herself as as a woman and Latina herself. So I would dare to say here that we are definitely a minority, and I would really like this to change, right? So there are more women in physics, but also more Latinas in physics. Okay, so I'll get into the whole thing here. I would like to start by talking about me, so you get to know me first, and then we can talk about my academic journey and my research and so on. But me, so I'm Mexican. I was born in Mexicali, so here, so this is San Diego here. I'm not sure if you can see my mouse, but this is San Diego, and I was born and raised here in Mexicali. This is a border city. So basically, if you take the 8th, you will get, and you drive 2 hours east, and then you go like half an hour south, then you get to Mexicali. So I was born and raised there, and then for my undergrad, I moved to Ensenada, where I studied physics. And I actually recommend, if you want to go visit Baja, don't go to Tijuana. Tijuana is ugly, but you can always go to either Rosarito or you can go to Ensenada. I would recommend like 10 times more to visit Ensenada, of course. I also like K-pop. My favorite K-pop band is Stray Kids. My favorite food is sushi or so shrimps, in general, shrimps. During the pandemic, I became crazy, I would say, and I used to make lives on Instagram, reviewing cereals. That was very entertaining. I had like 10 viewers, so I was very popular. I guess one of my goal dreams ever is to visit at some point Naruto's village in Japan. That's like a goal for me, like a dream of mine. I got married 2.5 years ago, and like the theme for the wedding was like the universe, and so that's why you can see here the cake. It's supposed to represent the universe. We even had astronomical observation during that day. If I'm not mistaken, we got to see Saturn with the telescopes, and there were moons like here and there, and so it was really nice. And yeah, in case you don't know, because I don't think we have mentioned it, but Leonardo, who's the next speaker, and I are married. So that's why our wedding was like very nerdy. And I added here Homer Simpson because in principle, I mean, he's not a nuclear physicist, but he works on nuclear physics stuff, right? So about my academic journey, so before wanting to become a physicist, I wanted to be a doctor, but a real doctor, not like the doctor I'm becoming now, like a real doctor that cures people and so on. But because of many events happening during high school, I discovered the world of physics outside the classroom, because when we do physics as high school students, we get a very short view of physics in general. So I find very hard for high school students to get interested into physics with what we see in our classrooms. So generally, people that are interested in physics would do something outside the classroom. They would get to, I don't know, participate in like scientific fairs, like outside or schools or so, which is kind of what happened in my case. I participated in the physics Olympiads, and that's how I discovered the real physics, right? So here I was 17. So this is San Pedro Martyr Observatory, which is in Baja. So it's like actually in the middle of Baja. And so here you can go and visit. This is the National Astronomical Observatory, and it's used by all the astronomers in Mexico, and sometimes from like international astronomers as well. So this was like my first encounter into like also real experimental physics. And then when I got into my first year of undergrad, I discovered this group, which is Sociedad Científica Juvenil. Basically, it's just a group of like many young students that they like to work on or they are interested in science. So some of them are already into an undergrad program. So some of them were studying biology or like computer science, math, physics, and so on. But we also have high school or even middle school students at that point. They were interested in science. So we would do like outreach for free, of course. And then this was my first encounter. I did a summer in Mexico City in the Instituto de Ciencias Nucleares, so basically the Nuclear Science Institute in UNAM. So this was my first encounter into nuclear science, and I was like, okay, this is definitely what I want to do. And then I did an academic exchange to Italy. This is also the first time that I got to spend some time working on the development of electronics, like PMs and so. And then I did a master's at McGill University, so I lived a few years in Canada. And this is the site here. This is the site where Nexo is going to be built. I'm going to talk about Nexo in a bit, which is the experiment I'm currently working on. And I also, like after returning from my master's, I also got the opportunity to teach a few courses for the energy engineering program and the material science program in Baja. So these were my students from the material science course. So here we are at the Nanoscience and Nanotechnology Center in Ensenada. If you want to meet the center, you can just Google, like it's called CNYN UNAM. So you can get to see the research that is being done being done there. So basically here we're just visiting. And this is what I currently do. I'm gonna talk about it in a bit, but this is at UCSD. And some other activities that I usually do is so for science, I'm really involved in all these groups where women in physics are involved pretty much. Or if we talk about caring about the environment or make, how to say, if we need to save energy, for example, or this kind of like climate change, I would say, approach for physics. So basically, this was a forum on how we as physicists, we can also make a change, right? When we talk about climate change, because it's not only for individuals like in our house and so, it's like everyone, also at work, we should all be thinking about it, right? Okay, so now I want to start talking about my research. So maybe we can start with a very brief overview on neutrinos. So if you don't know what neutrinos are the second most abundant particle in the universe, just after photons. Neutrinos are neutral particles, that's why they call neutrinos, but they are also very small. So the word neutrino comes from the Italian, so that's why it's called like neutrino. And it means like a very small neutral particle. We know that neutrinos are leptons. So if you take a look at the standard model of particle physics that you see here, all these types of neutrinos that we know about now are leptons. They interact weakly, so there are 4 forces that we can, or 4 main interactions. So we have gravitational interaction, we have weak interaction, electromagnetic interaction, and like strong interaction as well. So basically neutrinos would interact through this weak interaction, and they have a very small mass, as I said before. So in the past, we used to think that neutrinos had no mass, just as photons. So photons are massless particles, but we now know that neutrinos have a mass, but we don't know what the mass of these neutrinos is. We know a few properties of them, and we kind of have a hint on which range the mass of neutrinos should be, but we don't know a precise value for the mass of neutrinos. And actually, these kind of experiments that I'm going to talk about in a bit would give us a better idea, or maybe even a very precise number depending on our results. So we have 2, I just added here 2 main questions about neutrinos, but probably we have way more questions regarding neutrinos because we don't really know much information about them. The fact that they are neutral, and with this very small mass, it makes the whole thing harder to detect or to know about, to know stuff about them. So 2 main questions. We don't know if neutrinos are Majorana or Dirac particles. So basically, if neutrinos are their own antiparticle, just as photons. So photons are their own antiparticle, but for example, positrons and electrons are their antiparticle, right? And they are 2 different particles. So we don't know this about neutrinos. And the other thing here is that just as we have conservation of energy, conservation of charge, and so on, which are physical laws that they should be conserved always, we don't know if neutrinos could violate lepton number conservation, because since we have leptons, so each lepton has a lepton number assigned to it. So sometimes, as I'm gonna mention in a bit, theoretically, we think that this might not be true, that I mean that neutrinos can violate lepton number conservation. Okay, so now that we know a little bit about neutrinos, I want to tell you about neutrinoless double beta decay. So basically, double beta decay is a type of decay, which means that you have an isotope with Z number of protons, and it would decay into another isotope that we can call its daughter nucleus, let's say, right? And then here we would have Z plus 2 protons in this case, which means that if you take a look at the periodic table and you see, let's say, one of the elements, you will be having a decay like 2 spots. If you count like 2 spots from the one that you're looking at in the periodic table, that's the new element, let's say, after the decay, right? So this isotope with Z number of protons would decay into another isotope with Z plus 2 number of protons, plus 2 electrons, plus 2 antineutrinos. This is a double beta decay. The normal one, the one that Maria Gopper-Mayer, who was the second woman ever in winning Nobel Prize in Physics. And she proposed double beta decay, right? The one that I'm telling you about here without this red line. And actually, if you go to UCSD, she worked sometime in UCSD, and the physics building is called Mayer because of her. And you can see and if you go to the 4th floor, I think you can find like many pictures of her while she was working there. Okay, so this is a double beta decay, and basically we know that double beta decay exists. We have detected it with experiments and so we know that it exists. But what we don't know if the neutrinoless version exists. So basically, imagine that we have this same decay here, sorry, but without the emission of these 2 neutrinos. And in principle, since these 2 don't have charge, they are neutral particles, right? Charge can be conserved here. So that's I guess we can say that charge conservation would be satisfied in that sense. Conservation of energy can also be satisfied because I mean you can just split the energy, right? Every like I guess every electron volt of energy that you have here, you can split it into these 2 items here. So it makes sense. But if this is if we have this decay here without the emission of these antineutrinos, which, as I said again, this theoretically makes sense, we would not conserve lepton number here. So if you don't have these 2 particles, then you would not conserve lepton number again, which violates what we know about the standard model of particle physics. And how do we know that? So in principle, these electrons are leptons, and these 2 antineutrinos are leptons. So when we have double beta decay, they would cancel each other, the lepton number. But if we don't have this, then we have an imbalance. So we have lepton number equals 0 here, and we will have lepton number equals to 2, I believe, right? So the thing here is that we wouldn't have the same thing in one side of the equation and in the other side. And you might be wondering, so okay, so this is what we want to detect, but I mean, how difficult is it to detect it? So this is the signal that we get for the double beta decay, the normal double beta decay that we know when we have the emission of neutrinos. And this peak here, that this actually enlarged for you to see it, is the signal for neutrinoless double beta decay, which means that if we want to detect this, event, then we need very, how to say it? I mean, a very accurate, I guess, experiment, but also very low background experiment. So we need to get rid of all background to make sure that you can detect this signal here, because in principle, what you are detecting is just this decay, which means one single atom here, one single atom decaying into another isotope here. And that sounds like very difficult. So you have to create a detector which would be able to detect one single atom, if that makes sense. Okay, so there are a few experiments also, there are a few experiments looking for neutrinoless double beta decay. So one of them is NEXO, the one that I'm currently working for. So NEXO is a big collaboration that aims to observe neutrinoless double beta decay for the first time in the isotope of xenon 136 decaying into barium 136 plus the emission of 2 electrons, right? Because if neutrinoless double beta decay exists, you won't have the emission of neutrinos, right? So this is what we expect to get here. So there are, as I said, there are a few experiments looking for for neutrinoless double beta decay, but not all the experiments they are looking for the event in xenon 136. So there's another event called, I think, Majorana demonstrator. I'm not sure if it's still running, but I think they are looking for it in germanium decaying into selenium. There are other experiments. I think it's called Legend. Legend is also, maybe it's the same one. I'm actually not really sure, but I think it's also looking for this this phenomenon in germanium. There are so in principle there are a few experiments, as I said, and not all the elements are are allowed to decay through this double beta decay. So there are just a few of them in the periodic table that makes sense for them to decay into like this double beta decay. So this is the experiment that we have. The plans that we have for Nexo, because Nexo is still not built, but the plan is to, in a cryopit, I don't know if you remember the picture that I showed you before, but basically in a snow lab. So snow lab is an underground lab in Ontario in Canada, which is, I think, 2 kilometers down the surface. So down the ground, you take an elevator and then you get into a snow lab. So basically that used to be a mine, and now it turned, I guess Canada turned it into a lab. And there are a few experiments in there, and one of them will be Nexo in a few years. I think the building of the whole experiment is scheduled to start in 2030 if funding, I guess, is given, because I mean, as you might know, the situation currently is very difficult. But if everything goes okay, then in 2030 we should be starting the like building of the experiment. So the experiment consists in a TPC. So a TPC is a time projection chamber, which is going to be filled with liquid xenon, enriched to 90%. So it's xenon 136 enriched to 90%. And then, so here you will have 5 tons of liquid xenon, and outside we have an inner cryostat. So we have a refrigerant here in order to keep the xenon in its liquid state. And And then we have a vacuum here in the outer cryostat, and everything that we have here, which is a 13-meter diameter tank, is filled with water that serves as a shield. And that's the reason why we are building Nexo underground, because we want to avoid background from coming from cosmic rays and all of that. So basically, we use the earth, I guess, as a shield here. And then when we say that we have a sensitivity of 1.35 times 10 to the 28 years, it means that we expect that this is the half-life of the decay. So basically, that's the reason why we have 5 tons of liquid xenon. So imagine in 5 tons of liquid xenon, how many atoms you will have in there, like billions of atoms, right? In principle. So if you know that this is the half-life, you expect that at least in 10 years of running, since you have many atoms in there, at least one per year or so should decay, right? So I think Nexo will be running for like 10 years or so. So we expect that during this time, we will be able to detect, as I said, at least, one per year, one event per year. That's the goal. But let's see, right? So what I currently work on for the next experiment is the barium tagging technique, which since removing background is very important, this barium tagging technique, what the goal is to discriminate against all backgrounds except the 2 new beta-beta decays. So basically the normal double beta decay, I guess. And if we do that, this is how we improve the sensitivity. So that's why we are working on it. So the barium tagging technique is not part of Nexo as it is. It's more like an upgrade. So once the whole thing is running, and so we plan to add the barium tagging technique so we can improve the sensitivity of the experiment. So Nexo is a big collaboration. There are people working in Nexo in Canada, in the US, in South Africa, if I'm not mistaken, in Europe as well, and so on. And so there are 2 teams here working on the barium tagging technique in Canada and in the US. So for the barium tagging technique, Canada has one approach. So basically, they have liquid xenon, and from liquid xenon, they kind of artificially add barium, and then we try to extract it, turning liquid into gas. And then we reduce the pressure of this gas until we reach vacuum in order to, extract this barium, right? And be able to detect it, because at the end of the day, that's what will happen in EXO. So inside the TPC filled with xenon, one of them will decay into barium. And what we wanna get from there is will decay into barium plus 2 electrons. And what we are detecting there in principle is the charge from these 2 electrons and the light that will come from these 2 electrons. But also, to make sure that this is a double beta decay, we need to make sure that the barium that we are detecting comes from one of these decays, right? So that's the reason why we are doing, again, this barium tagging technique, because we are grabbing the barium coming from the decay and making sure that it belongs to the decay, right? So what I do, I use is a slightly different approach. Instead of going from liquid to gas, we have liquid xenon and we turn it into solid xenon. So basically, we freeze xenon. And from there, as I said, we artificially add barium ion, and then we want to make sure that we can extract it, right? So this is kind of the setup that you're gonna find at UCSD. As I said, our goal is to freeze this liquid xenon, and then once we freeze this liquid xenon, we want to make sure that we can control the thickness of the eyes, and that we can visually see it in principle. So we are building a few sensors in there to again to measure the thickness of this solid xenon, and we have added a few components here and there to visually see the existence of liquid xenon. So for that, basically we have a cryostat, and we have a cryogenic probe. So in principle, the xenon that is going to be frozen and that we are going to extract and analyze, and so it will be formed around this tip here that you can see here. So basically, we have a probe that will be introduced in liquid xenon, and then we pull it up, and then we study the formation, as I said, of this liquid xenon. So how do we cool down the liquid xenon? Our team at UCSD freezes the xenon with liquid nitrogen, but the team in Colorado, I think they freeze the xenon using helium, if I'm not mistaken. Yeah, so this is how our setup looks like. So we have, as I said, the cryogenic chamber, which is this one here. This number 2 is our cryogenic probe that is introduced into a small chamber inside this cryostat, which at some point is going to be filled with liquid xenon. So we right now we are like a step before adding liquid xenon. So we have xenon gas in there that we freeze around the tip, and that we are trying to control the thickness. And so once we are done with that, then we add liquid xenon. So we do that because first, xenon is very expensive. So if we add xenon gas, would be like a very little volume compared to if we add liquid xenon, because then you need more volume of xenon. But also because I mean, adding liquid xenon is kind of dangerous. You need to control the temperature or so, because if you don't control the temperature, I mean, the liquid xenon will expand. I think the volume of liquid xenon expands like 800 times in gas, so you can imagine how dangerous it is if you don't have a proper temperature control for that. So this is basically the setup here. This is the liquid nitrogen tank that we have for freezing the xenon. You can see here like a ice around the hose in here, and this is the xenon tank. Okay, so yeah, and some of the things that we want to do first is to be able to control the temperature of the tip. Since we want to freeze xenon, we want to make sure that we can stay at one single temperature. So for example, here I wanted to stay around minus 100 Celsius, which is kind of I think it's minus 110 Celsius, the temperature for freezing xenon. Yeah, and so these 3 lines basically represent 3 different positions that I'm going to show here. So the probe here, we have a detector here. So actually this Kapton tape that you can see here, there's a detector in there that measures resistance, but it turns it into temperature. That's how we measure the temperature in there. So we want to make sure that the temperature at the tip, the ceramic that we have in here, and the probe are different, because in principle, we only want to freeze the tip. We added this ceramic here that works as an insulator, so that way we don't get the whole probe frozen. And so this is what you see here. In principle, what we want to get, this blue curve here represents the temperature at the tip. So if we get that curve going into the temperature that we want, so in our case, like minus 100 or something, then it means that it's fine. And then here, I mean, we also study the I guess the amount of liquid nitrogen that we get into the probe. So we also know how much liquid nitrogen we need to freeze the probe for a certain amount of time. That's also useful information for us. And then, so last December, we had our first solid xenon observation. I want to show you here. Let me see if it. So this is the tip, and this is inside the chamber. And you will start here to see eyes, like a formation around the tip. I'm not sure if it's clear to see it in here. So for example, here I'm gonna close the liquid nitrogen and you will be able to see how it melts. You saw that. So in principle here, you see it's kind of thick around the tip. So you have some xenon ice, which is transparent. And actually that's something that we want, that the xenon is transparent as well. And here what we have, you cannot see it because in principle, xenon is transparent, but we have added 1.5 bar of xenon gas inside the chamber, and then we freeze the tip, and all the xenon like starts coming to the tip in there. Okay, and then I want to show you. I'm almost done here. So what you see here is okay. What you see here is xenon, liquid xenon boiling, pretty much. This is not water. And what you see below is cryoASIC. So basically, these are detectors of like charge detectors for later on when we want to detect these two electrons. We want to make sure that these sensors, of course, work immersed in liquid xenon at these very low temperatures, right? So that's the reason why we make these tests to make sure that they work after they are immersed in liquid xenon. Okay, so then this is just I guess a diagram of the Nexo collaboration. As I said before, we have like many institutions working on some parts of Nexo. So it can be on the wire timing technique, or working on the development of PSI-PMs or the cryo-ASICs, so the detectors of light or the charge detectors or working on simulations as well. Yeah, so there's a lot of stuff to do for Nexo, and I'm not sure if you can see here, I added this smiley face. This is the location where Nexo is planned to be in the next couple of years, I guess. But yeah, this is where Nexo is gonna be. And that's it. If you want to know more about Nexo, you can shoot me an email or you can add me on LinkedIn. I'll be happy to answer your questions, and thank you.
Thank you very, very much.
Shall I go next, or are we waiting for questions here? Okay.
Give me one quick second. Does anybody here have any questions for Melissa before we move on? No? Okay. Okay, we're ready.
Okay. That will be hard to beat.
Okay,
I'll
let
try to
me-
be fast. Yes, I'll try to be fast because I know we have like 20 minutes left, right? So I'm going to share my screen. You let me know if this is working. Okay, are you seeing my screen now? I cannot see you, so if someone can talk.
Yeah,
Yes, no?
we see a PowerPoint.
Perfect. So this should work perfectly. I'm on my iPad, so I think it's a lot of power for my iPad right now. Melissa, you think you can share maybe? Here it is. Okay, perfect. All right, so as you mentioned before, my name is Leonardo Espinoza. That's my full name. I'm a PhD student at the University of California, San Diego, too. But I'm working in the mechanical and aerospace department, okay? And what I do is basically, well, let's start with this. The name of my talk is basically From Equations to Exploration, mapping the routes around Enceladus. So I'll go quickly with my introduction because Melissa said many things that I was supposed to say here too, but I'm just going to repeat some past ideas here. So that's me. You can see me here, but that's another picture of my body. Okay. As Melissa mentioned here, I'm from Ensenada. Ensenada is actually here. That's about maybe 2 hours, 1 hour and a half from San Diego, depending on the traffic, correct? It's the second city after, I mean, you have Tijuana and then you have Rosarito and then you have Ensenada here. I actually grew up there and I studied there my undergraduate studies in physics and I did a master's there. I got that in a second. That's my dog. His name is Jupiter, and that's fun because I'm working with stuff around space. I mean, space stuff around planets, right? So this is Jupiter. I am a really huge fan of Marvel, and today there were a release of the Avengers Doomsday Cut, and I'm super excited about that. I'm a real fan of Nintendo too. My favorite video game is Pokemon. If you play Pokemon Go and you wanna add me, send me an email. I'll share my username. My favorite movie, Shrek 2. I'm not sure what to expect about Shrek 5. We'll see. And I really love cooking. I don't like to do the dishes, but I love cooking. And that's my favorite food, actually, like pizza. Easy, right? Okay, I studied in the Autonomous University of Baja California in Ensenada. I really love do like outreach, public talks, public experiments. That's a picture of us like 10 years ago when I was an undergrad student. I think Melissa is also there somewhere. That's the name of the group Melissa mentioned. So she already mentioned that, so I'm going fast here. That's a presentation we gave about our group in the International Conference of Physics Students in Germany in 2014. So I was an undergrad there, I think it was second or third year studying physics, and we presented what we used to do in Mexico at that time. For my thesis, my undergraduate thesis, I worked in the UNAM and the National Astronomical Observatory, what Melissa mentioned before. And I used to do astronomy. I was really passionate about space when I was in elementary school. And then I said, okay, what do I need to do to be an astronomer, right? So the first thing you need to know is physics. So that's the first thing I did. And my thesis was about astronomy. So we work with that nebula, which is, the name is NCG 2346, or also known as the Butterfly Nebula. And what we used to do, basically, we computed the morphology and kinematics from data taken in the observatory there. It was super interesting, was super fun, but I realized that when you go to the observatory, that's super cool. But when you come back and you work on your computer, that is not so cool. So I still liked the space at that time. So I tried to find other ways to still work in space. And that's why I decided to study what we call in Mexico like a specialization degree. I think that in the United States might be like a diploma. Or for those who are in the university, that will be like the major, right? So I did a specialization degree in aerospace industry in Ensenada too. And what I did there was basically to create a device to join a rover and a drone. And you can use both for space exploration, for example, in Mars, right? You can use both for protection for in the case of an earthquake, for example, right? And also for climate change. You send the rover and you send the drone, you take pictures from there. But I didn't work with the drone or the rover. What I did was the device to join them, okay? And then I decided to study a master's degree also in Ensenada. And the problem was basically applied physics, something like that. In the same university where I did my undergraduate students. And what I did there was basically I worked with a CubeSat, that's a small cube, which is basically a satellite. You have a lot of sensor there, and usually the universities and space agencies use this CubeSat to they send these cubes to space because they are really cheap compared to the big satellites, right? What I did here was basically mathematical modeling, all right, and simulations to see how we can model the satellite. But what I want to tell you is about my current research here at UCSD, all right? And so yes, I'm a 4-year PhD student. Hopefully I will be a PhD candidate next month. We'll see, finger crossed, all right? What I'm working is with the three-body problem. I don't know if any of you know this book, all right? This is a good book. I recommend you should like science fiction, physics, astrobiology, and that kind of stuff. Or maybe you know this Netflix series, right, about the three-body problem, which is actually based on the book. Both of them talk about, without spoilers, right? It's just in the title, the three-body problem. So that means you have three bodies in astronomy or in space. Could be 3 planets, for example, or maybe 3 stars, right? And they move around each other, basically doing weird stuff. I'm going to talk about that in a bit. But if you ask me about they bought the series or the book is much better because in the series, all the scientists, they have a lot of money, which is not usually true. They are super cute. I mean, they are beautiful, right? Which is not always true, right? But this is what I do, basically. We have 3 bodies here. This is a simulation I took from Wikipedia. Basically, we have 3 bodies orbiting each other, basically. But what I do is basically we apply this problem or the physics behind this problem to Saturn and Enceladus, all right? So you might know Saturn. This is one of the biggest planets in the solar system. And the good thing about Saturn, besides the ring, is that we have this moon called Enceladus, which is the moon we have there. And what I study is basically the restricted 3-body problem. And it's called restricted because we assume one of the 3 masses is massless. I mean, the mass is really small compared to the planet or the moon in this case. And we assume that mass, or the test particle, is basically a spacecraft, okay? The cool thing about Enceladus is that we call this icy moon because we have this frozen surface, right? And under that frozen surface, we have water, liquid water, right? And if there's liquid water in space, you can imagine many, many things. The first thing I can tell you is that this is important for human space exploration because in a few years, many, many years, if we can go there, we can collect that water, for example, and we can drink the water, right? We can separate the hydrogen and the oxygen, and we can use the oxygen for us. We can use the hydrogen and the oxygen for more rocket fuel, for example. But most importantly, we have liquid water there. That means that there we can find life, okay? Maybe not a whale, maybe not a fish, but maybe some bacteria, maybe some, I don't know. I'm not a biologist, okay? But you got the idea. And the most important thing about Enceladus is not in this picture, but in the south pole of Enceladus, we have this water plume that is releasing the water of Enceladus used to space. So if you want to go there, you don't need to drill the surface. You can take samples of water from this water plume and you can analyze that, right? And that way you don't contaminate basically the interior of Enceladus in the case we have any bacteria or whatever, all right? So that's why we are studying this problem. What I'm doing right now, for example, is this kind of simulation with the 3-body problem. And what we have here in this picture is basically we have the moon, Enceladus, and in blue, what we have, at least for this time, for time we run the simulation, in blue we have orbits that are just orbiting Enceladus, and in red we have those orbits that are colliding around Enceladus or are colliding on Enceladus. And this is super important. And besides the astrobiology component here, this is super important in the term of physics because it's a really, it's a, a huge perturb problem. I mean, Enceladus is really small compared with Saturn, and Saturn is really close to Enceladus. So the perturbation you have due to Saturn, the gravitational perturbation and other perturbations, such as the gravity harmonics, I mean the shape of Saturn, that produces a big perturbation in your spacecraft. And you need to know what orbits are stable, what orbits are not stable, okay? Because that way you can save money and you don't collide with Enceladus, you save money and you save energy too. Okay, so this is what we are doing basically. And this should be a video and it's working perfectly. So what we have here, for example, is what we call a halo orbit around the south pole of Enceladus. And basically in red, we have a simulation without gravity harmonics. That means the shape of Saturn and Enceladus, the mass distribution, I mean. So when you see, when we don't have any perturbation, we have basically the full orbit, right, around Enceladus. When we add the gravity harmonics, let's see if I can run this again. When we add the gravity harmonics, the orbit, at least for this simulation, for this initial condition, the orbit just goes away from the system, right? So this is the type of orbits we're studying basically in our lab. And here, this is a new image I basically obtained last week. This is a little bit more complicated, but what we are using here is a technique in nonlinear dynamics that we call the fast Lyapunov indicator. We are basically checking here for stable and unstable manifolds. Just quickly, the manifolds, the way I like to explain that, and those are like natural trajectories due to the geometry and physics in our system. So what you have here in the blue shape we have here basically, in blue, when you are close to one, right, in the color bar, that means that you are stable in your orbit. If you stay there, if you are there, you're going to stay there. But in those zones where you are close to, for example, yellow or green, that means unstable, right? So if you are there, you're going to move away from that position. So basically here, you can use the unstable manifolds or the stable manifolds basically to move free around the system. This is an XY, what we're working right now is in 3D, like representation of the manifold for this. And this is the main like research with, at least I do, right? With the three-body problem, we applied nonlinear dynamics techniques, physics techniques in our system, like the fast Lyapunov indicator, Lyapunov exponents, Poincare maps, and many other interesting things here. But yeah, that's basically the idea. I know I was fast, but I know we have no time for that. So what's next? Like what I plan to do after my PhD, and the truth is I have no idea. I'm pretty sure many of you are in the same situation that you don't know what to do after your studies, right? But I know, for example, well, let me go back a little bit. I decided to study in UCSD in San Diego, particularly because it's close to Baja California, and I'm from Baja California, right? And there are not too many collaborations in the aerospace engineering field between the United States and Mexico. So this is what I'm trying to do right now. Like I'm trying to involve students in Mexico to come to UCSD and do research. I usually go to Mexico and give some talks, public talks about what I do, what we are doing in our lab, right? So this is something I want to keep working on. I would probably do a postdoc because that's the easy way, at least for me as an international student, if I want to stay doing aerospace engineering. And maybe in the future, I can join to industry, aerospace industry, I mean, and to work in these missions, space missions, actually, right? But that's not sure yet. I mean, I'm not sure about what to do. But let's see what happens, right? So far, I can tell you that the next step, right, in my career is my PhD, my candidate's exam, basically, all right? But if you have any questions, you have the information, you have my email, so you can ask for my email and send me any questions you might have about aerospace engineering or the program I'm studying right now, and I'll be happy to share answers, at least the answers I know with you, all right? And I guess this is all.
Thank you both so much. I just want to
Thank
check
you.
with everybody in the room. Does anybody have any questions for the speakers? No? Okay, awesome. I think one of the, sorry, my Siri is acting up on me. I have one question before we let you go for the both of you. So, just because you talked so much about your research and your background, what do you feel that you would like to gravitate towards? Is it more so teaching, or do you know that you want to stay in research? Because I feel like a lot of people who pursue their doctoral degrees, they do sometimes a little bit of both, and sometimes they stick on a certain path. So like what has piqued your interest so far, like in working with your PIs, your advisors, working with faculty? Is that something that kind of like interests you, or do you know as a fact that you want to remain just pursuing research?
Well, I go quickly because I think that at least for me, for my field, it's hard to join industry because I'm an international student, and almost all the companies that are working on this field, they have contract with the government, and if you have a contract with the government, you cannot hire international employees, right? So that's why I plan to keep in academia. But once I get maybe the green card, whatever, I'll try to do definitely something in industry, right? I really love teaching, so that's for sure. So if I go to industry or no, I'm pretty sure I won't stay like teaching some classes like physics or aerospace engineering classes, right? But that's the answer, basically, Melissa.
In my case, I love teaching. As I said before, I've worked as a teacher, and I really enjoy it. I also enjoy to be a TA. So I would really, I don't know, like I feel like I love that part, but I also love money. So I don't think I'm gonna get money if I just teach, to be honest. And I feel like at least my research is very applicable to to industry. I'm really interested in going into industry. I've never done anything in industry. And I would really like to do an internship during my PhD to make sure that that's the path I want to follow. Um, but yeah, I mean, I'm not sure yet. But the good thing about my PhD, I would say, is that I get to learn many skills. I have now a lot of skill. Like I know how to teach, like I know how this, I guess, pedagogic side of physics. I also know how to do like experimental stuff, like in terms of very engineering in like use solid works and so that not many physicists would do because I'm an experimentalist. I also do like software stuff. Like I also do some programming and so like I have plenty of things that I can choose if I want to do this or that. That's what I think is really good about my program. Because some physicists, for example, would just do theory and they want to stay in academia, which is fine. In my case, I don't know, so I'm very happy that I know how to do like at least a bit of everything. So if I get interested in something, just I can just learn a bit more about coding or a little bit more of you know, like designing parts or so, so I can get into one specific area. But I mean, like summarizing, I think I want to incline towards industry in my case.
Thank you so much. It sounds like you have like you're very well-rounded to where you could choose to do both. So thank you both so much for spending some time with us, with the students here at City College. You both are like this awesome power couple. Like I didn't know that you both were married. Like that's awesome. So one of the things that we do here at City, we started something called the Summer Bridge Program. And so basically like what you did today, which was fantastic, just talking to the students about like your research and your background and what it is that you do. Because a lot of the students here, unfortunately, there's a lot of gateway courses that keeps them from transferring to a four-year university. And so my job is as a coordinator is to help to create programs, to introduce them to folks like you who are actually doing the thing, right? Who transferred or maybe just like landed at the university or are working in grad school. already to kind of keep them interested and to spark their curiosity. And so we started the summer bridge program with the idea of one, sparking the interest of students about STEM, and then two, kind of helping the students who are already in STEM kind of figure out a really good detailed plan on how to transfer and how to either land a career or an internship. And so we'd be honored if you're interested. I can reach out to you after. We have 6 days of the program. So if you both have a day that maybe aligns with your schedule, if you'd be open to it, we'd be happy to have you here on campus. And that opportunity, fortunately, is a paid opportunity, which I'm really happy about. So it's 6 days and we hope to have like different people for each one. So if there's a day that works with you, we would love to have you here on campus.
Yeah, for sure.
Yeah, sounds good. We can follow it up, I guess, through email.
Yeah, absolutely.
Thank you. Well, thank you for your time again. Just a last round. Does anybody have any questions before we go? We're good? Okay, happy? Okay, cool. Well, thank you, everybody. It was great to have you and have a great rest of your week. And we hope to see you soon.
Yeah,
Take care.
bye-bye. See you.
You guys know if Chris is gonna be here?